Welcome to the study of geometry. We are going to begin today with Unit 1-1. The title is Points, Lines, and Planes. Points, Lines, and Planes. We start out with geometry with some undefined terms. We go from there to definitions, and we go from there to what we call postulates and theorems, which are rules. The three undefined terms that we begin with in geometry as we begin to create a language are point, line, and plane. The reason they are undefined terms is because they represent something that in reality doesn't exist other than a location. In algebra, we talked about the XY axis, and we would have points on the grid like 1 and 2 for X and Y. And we may have plotted a point, and we said, okay, there exists a point in the location where we would name the X first and the Y second, and we would give it the coordinates of 1, 2. You may say, well, that exists, I can see it, and we could call that point A, but then we would say, but in reality, point A is not that big around, it's really just a smaller dot than that. And it's really not as big as that black dot, it's really a smaller dot than that, because in reality, if we drew the line that went through that 1 and the line that went through that 2, those lines would be like taking a pair of scissors and cutting. And if you cut, no paper falls out. And if you cut, no paper falls out. And right where those two cuts met would be that location. So that location really doesn't take up any size. It doesn't take any space. We just have to color in a dot so we can actually see it. The line that we made the cut with the scissors doesn't take up any space either. It just simply separates two flat regions. And then a plane would be like taking a knife and cutting through a cake. And so it's going to separate that cake into two halves, you see. So we're talking about boundaries and locations that in reality don't take up any room. They're just telling us exactly where a minute specific location is. Okay, so we name a point by a capital letter. As we did in algebra, we would have said, well, maybe there's a point here, point A, and we would say that the coordinates of that point A are 1, 2, where the 1 was the X move and the 2 was the Y move, known as the abscissa and the ordinate, and together the coordinates of the point. We could name that point that I just put with just point A, or we could write out the word point A. There might exist another point B in another location that we could name by writing out the word point B. And again, we used a capital letter. A line. A line is, as I talked about, is just like taking a pair of scissors and cutting down through there. And when you do it, would separate the paper into two parts. You could see a distinction between the two parts, but yet you wouldn't see any paper fall out. And so it's an invisible boundary line there. And so a line is named either by 2 points on that line or by a lowercase letter. If we had a line such as this line right here that contained the points, point A, point B, and point C, then we can name that line by any 2 points on that line in any order that we wanted to name them. So we could call this line line AB, or reverse line BA. We could call it line AC, or reverse line CA. Or we could call it line BC, or reverse line CB. We also sometimes name a line using a lowercase letter if we're going to name the line not using points on that line. Line L, line M, line whatever, using a lowercase letter. A plane separates two three-dimensional figures. I guess that wasn't a very good illustration. I was going to try to draw two three-dimensional figures like pieces of a cylinder, and where you would take a slice out of that cylinder, and so that plane would be that circle slice between the red and the black, if you can visualize that happening in the middle of all that stuff I just drew. And so it's going to be a flat boundary that separates two three-dimensional regions. Now, that's not really a definition because the plane itself would take up no space as you slice that knife through there. And so it in reality doesn't exist except as an invisible boundary. We name a plane by a capital letter. We represent a plane with generally a parallelogram, and we would use a capital letter in the corner, or one of the corners of that parallelogram, to name it, like plane M. If we do have a polygonal region, then sometimes we will name a plane, a specific flat surface, by a polygonal region of points that lies on that surface. And so we may say, well, exists a plane that would contain these points on that plane in this order, N, O, Q, P. And normally when we name a plane by points on that plane, we're going to name them using capital letters for those points in either clockwise or counterclockwise order. We don't skip around. So we would say NOPQ, which later we're going to talk about rectangles, rhombuses, and squares. And so we might say square, NOQP, or rhombus, NOQP. Okay? So we have shown the existence of three undefined terms, point lines and planes, and really discuss them as being boundaries and locations. Now, once we make definitions, we went from undefined terms to definitions. And if we're going to make definitions, they're going to have to include one or more of those undefined terms, because geometry is a language that builds upon itself. Later, we will make definitions that contain even other definitions, so our language will grow as we go. Space. Now, when we think about space, one of the first things that you may think about is an open container like a can, which we know this to be a sphere. And inside that could be filled up with liquid as we get higher and higher into that cylinder. And you may say, well, we filled it partially up, but there's some space left at the top that we haven't filled up. And so when we think of space, we think about the room that is within a three-dimensional figure. If we think about all such space, then we would think, well, there's some points that exist in this region that haven't been filled up. And if we think about the universe and any such points that would be contained within the universe, then that would be what space is. We talk about outer space as being everything out there past where we think our airplanes go and that kind of thing, or the birds fly. And so space then is the set of all points. Space is the set of all points. Or you may think of it as every location that exists. Every location that exists in our universe. Okay? We may, for just a moment, talk about one other thing. A point really has zero dimensions. It really doesn't have length, width, or height. A line begins to have what we might call length, even though it has an infinite length. It has one dimension length. And as we get to thinking about a plane, we start thinking about a flat surface which has length and width. And when you put length and width together, we have something in little square blocks called square units, which is considering the area of that plane figure. But here we have two dimensions. We have length existing and width existing together. When we think about space as something contained in a three-dimensional object, like I talked about with that cylinder, the space within something like that, then we think of space as the existence of three dimensions, length, width, and height together. So space kind of gets us to thinking three dimensions. Plane has us thinking two dimensions. Line has us thinking one dimension, and a point has us thinking of no dimensions at all. That's going to become important later as we make other uh, definitions and things to come. Collinear points. If we really understand the English language, then we can know what these definitions are just by knowing what the parts of the words are. Collinear. Co really means together. Co-pilots pilot the same plane together. Linear, well, we know that's line. And points, well, we know that's points. So collinear points are points together in a line. Points together in a line. So it's not a tricky definition. It's really a common sense definition. Collinear points are points together in a line. The points A, B, and C, then we could say are collinear points because we can see that they are points together in a line. We can see also that there's not a line that exists that would contain points A, B, and C. Not one line would contain all 3 points. So we could say that A, B, and D are non-collinear points. Which would be points not together on a line. Points not together on a line, non-collinear points. If collinear points are points together in a line, then coplanar points would be points together in a plane, points together in a plane, are in the same flat surface. And so if we think about this flat surface that I've drawn there in red, then you can see that points A, B, C, and D all lie on that same flat surface. So we could say that A, B, C, and D are coplanar points. If we consider point E, you can see that point E is on this vertical plane. It is not on the same horizontal plane as those points. So if we chose 3 of those points on that horizontal plane along with point E not on that same horizontal plane, then we can see that A, B, D, and E are non-coplanar points, meaning points not together in the same plane. We have 3 undefined terms, point, line, and plane. We have the first definition, space, which is the set of all points. We have collinear points, points together in a line. Coplanar points, points together in a plane. And now we get to the definition of intersection and our first postulate and theorem that follows from that concept of intersection. When we think about intersection, we would normally, as far as real world visualizing, maybe go back to 2 highways that meet. And we might call this road, road A, and we would call this road, road B. And we could say, well, there's a car X that is on road A, but it's not on road B. And we could say there's just a car Y that's on road B, but it's not on road A. And I could ask the question, well, where is the intersection of A and B? And most students would say, well, the intersection is where 2 things hit. If we think about intersection, and I really wanted a definition, then people say, well, this is where they hit. Well, that's not a good formal definition of intersection. Where do these 2 roads hit? It's more than that. Here exists a car on road B but not A. Here exists a car on road A but not B. If we place a car right here, car Z, we say it's in the intersection. Why? We say it's in the intersection because it is really on road B and it's also on road A. The intersection is the part of that highway that's road A and road B. It's a part of both. It's the part of the road that is common to both road A and road B. The intersection of figures is the set of all points common to both figures. Now, from algebra, we know from page 130 of the Algebra 1 text that I wrote, it says that the solution to a system of linear equations is the one point x, y that makes them both true, which is the point of intersection in the graph because solution means intersection, which means what is common to both. And so we would have an equation like y equal, I'll do it in red so it kind of matches. This red line could possibly be y is equal to a positive slope of x plus 2. And the blue line could possibly be in a linear equation with a negative slope that's just a little bit steeper. So maybe y is equal to 2/3 x uh, plus 4 or something. And we said the solution to that system was that one point, x, y, that makes them both true, which is the point of intersection in the graph. And we could actually solve with algebra and find that one xy that would make them both true. The fact that we could solve mathematically and prove that there is a point xy that exists as a solution to both of those lines is a mathematical process of proving it, and so we call that a theorem. So our first theorem of geometry, Theorem 1-1, says that the intersection of two lines is a point. The intersection of two lines is a point. Something mathematically that we can prove. Now, if we think about two planes, this vertical plane intersecting this horizontal plane, the that they actually had in common was that little segment across there. But if we consider the fact that this plane extends infinitely and this plane extends infinitely, then we would have to consider that the intersection of those would extend infinitely. And with our eyeballs and some thinking, we can reasonably conclude that the intersection of two planes is a line. Now, we didn't do that with some algebra solving skills or some rules that we put together. We used mental logic and experimentation to come up with this rule, and we call that a postulate. A postulate is a rule that's based on experimentation and mental logic, not necessarily derived specifically from another set of rules that we pieced together and proved it by some other mathematical facts that we already knew. So we have theorems that are built upon mathematical knowledge from the past that would prove that this is true. And we have postulates that are based on mental and visual uh, things and being able to experiment and prove that it's true. So, Theorem 1-1, the intersection of two lines is a point. Postulate 1-1, the intersection of two planes is a line. Well, that's lesson 1-1, which gets us started in building a language of geometry. In a moment, we will record going over the practice. So we're going to teach every lesson in this book. We will go over parts of every daily work portion. And then there's homeworks that look like the tests, and we'll go over those. And then that should have us really